Hello everyone, welcome to this tutorial. My name is Emerson Ahrari, I'm a Google Earth Engine expert. In this tutorial I'm going to show you how to monitor the air quality regarding to COVID-19 situation. So as you can see in this tutorial, you will be able to plot nitrogen dioxide for the metropolitan area and see how COVID-19 actually impact on the air quality. For example, in this tutorial, I'm going to use the New Delhi as a study area, and then you can see over the 2020 during the COVID situation, you can see the nitrogen dioxide decreased a lot, and also it's obvious and detectable in the Earth observation satellite data. Now in this tutorial, I'm going to show you how to produce such kind of plots and how to detect the effect or association between COVID-19 and air quality for a metropolitan area. This tutorial can be used for all metropolitan areas or big cities in all around the world where there is significant industrial activities and also dense population that actually helps you to understand how the nitrogen dioxide changes from one time to another time when some situations such as COVID occurred. So make a new notebook in the Colab environment and start programming. First of all, we need to call essential libraries to deal with Earth Engine in the Colab environment. Let's start with Earth Engine library and GEE map. Then we need X-array as another important library, allowing us to do the conversion between image collection and also the multidimensional data structure. So wait for a moment until the process is done. Next, go for pip install XE. Another essential libraries integrated with X-array and allowing us conversion between image collection and multidimensional structure. So as it is not built-in available in the Earth Engine, we have to install it first and then import it. Let's hide the description. So the next step, we need to make a bridge between Earth Engine and Colab environment using existing libraries. From Earth Engine library, start with authentication first and initialize your account information. First argument is the account ID. So how we can find the account ID? Go to the code editor environment, upper right, there is a option here. Go to project info, and here you can find your specific cloud project name. So let's copy and paste or type it. This is mine. And the next argument here is OPTURL that facilitates servers that facilitates image processing. So if you go to the code editor, if you go to the go on the net and search for XEE library, you will find a GitHub page easily including a detailed instruction about how to deal with XEE. And OPTURL is also available here. Just you can copy and paste it into your code. So let's run, and Colab asking you credentials or asking you permission to connect with your Google Earth Engine account. Now the permission is connected and we are waiting until it's done. Yes. From now on, we can bring Google Earth Engine capabilities in the Colab environment and do the processing based on. So, first of all, I need to select the region of interest. Let's make a new variable as map. Map equals to, from GEE map library, call the map function. So, make a user interface with the base map view. For example, with a train background. Let's print the map, and then you will have a user interface. This user interface allowing us to select the region of interest easily and without any challenge. This tutorial can be used for all around the world, but it is better to use this for dense areas and also the metropolitan areas. For example, in this tutorial, I'm gonna use the New Delhi as a case study to show how nitrogen dioxide changes after and before the COVID-19 situation. So here we have a New Delhi, and using the rectangle available here, I'm gonna select the city and also surrounding region. There it is. It's very simple, not a big deal. In the next step, I want to have this rectangle as a variable into the code. So a new variable ROI created equals to, from the map, select the last feature, draw last feature, and convert it to a geometry structure. Let's run. And now you will have a polygon with 5 vertices, allowing us to bound our satellite data for this specific region. In the next step, we need to call the nitrogen dioxide data from Sentinel-5. Go to the code editor environment, and through the search places and dataset, go for browse data catalog, and then go to all tags and find the air quality data. It's really straightforward, and you need to practice and follow all these steps to learn how to deal with the Earth engine and target data. Here, through the browse data tags, you will be able to find your data based on specific keywords. For example, now I'm gonna find the air quality data. Just type the air quality, and you can see 17 data set is available here. Most of them belongs to Sentinel-5, and here you can see the NRT, near real-time UV aerosol, and other products available. In this tutorial, I'm gonna have focus on the nitrogen dioxide, one of the actually air pollutants in the urban areas and also the dense region, shows the amount of the fossil fuels and industrial activities. So this dataset is available since 2018 to near real time, and also the image collection snippet also available here. Just copy and paste it. Nitrogen equals, make a parenthesis, paste the collection name, and then define the filter date and filter bound. I'm gonna call all the data available since 2018 to 2025. Then the filter bounds, allowing us to bound the data to the region of interest or the ROI. So as you can see, the various bands or several bands available here, but we want to have focus on NO2 column number density. Let's copy and paste it. Select the target band like this, and even we can do the change the name of the product or change the name of the band, because it's a little bit long, and also maybe it's a little bit difficult to call it everywhere in the code. So let's do like this. Select here, put it inside a bracket first, and then add the new name in the next bracket. For example, NO2. There it is. Let's print the nitrogen to see how many data available for this period of time. So the code is in progress, and here you can see the spatial resolution is around 1 kilometer, but it is resampled at 1 kilometer. The original resolution is around 7 kilometer. That's why actually we need to consider the 7 kilometer as a target resolution. Around 5,000 images available for this period of time, and temporal frequency is about 2 days. Because of multi-frame passing through the study area, you can see large number of images available. So we can also select only one image, because if you drop down to 5,000 images, maybe it takes actually a bit time consuming process. That's why I prefer to select only one image. To check the image name, you can see it's turned to NO2. Okay, now the nitrogen image collection is available. Now we want to use the XEE and X-array capabilities to do the conversion from image collection structure to a multidimensional structure. So here make a new variable dataset or DS from X-array, now called the open dataset, just like this. The target dataset is the nitrogen data based on Earth engine capabilities. We want to do this conversion. The CRS, the coordinate system, refers to should be EPSG 4326, refers to WGS 84, that is same for all around the world and no matter where you are working. So the next is about the scale. The scale is about the pixel size, meaning means the pixel size based on degree. 1 degree, 100 kilometer, 0.1 10 kilometer. As the original resolution is 7 kilometer, I prefer to resample it to 10 kilometer. For the air quality analysis, coarse spatial resolution makes sense. So, and the next parameter is the geometry. The region of interest should be the ROI. Here we are bounding our data to the ROI or the rectangle you drawed before. So now the data set is ready. From now on, the data set actually uh, exported from the Earth Engine format and now imported into multidimensional structure and Python API programming. Now we can do a lot of processing and also we can apply several machine learning algorithm even they are not available in the Google Earth Engine because these conversion allowing us actually to have a new format with a new capabilities that is not available that wasn't available before. So here you can see in the multidimensional structure, one dimension is time, another one longitude, latitude, and also we have one variable is NO2. And here you can have actually a short view, a brief summary about the data structure and the values available here. So in the next step, actually, I'm gonna make an annual image and show how the nitrogen dioxide changes in this area. So it's very simple to do when we convert the data to a multidimensional structure. So imagine that I'm gonna convert these 2 days data frequency to annual frequency. So the annual equals to get the data set first and do the resample based on time dimension. You can see a dimension we have is time and we want to have the time with annual frequency. So make a string format and calculate the average through the time. The average through the time, the average of whole year through the time. Okay, let's print the annual and also it takes a few seconds until the annual image created. You can see we have a large amount of data here, around 5,000 images available, and processing and analysis of 5,000 data definitely takes time, and it depends on the speed of internet and also the speed of internet and also amount of space, RAMs and disk available in the Colab environment, but sometimes it might take a little bit longer, but you must be a little bit patient when you are dealing with a large amount of data in the Colab environment. So, and sometimes even it may take 1 minute also. So as you can see, after 42 seconds, the annual average created. And now I can make a plot for the annual images and see how spatial value, how actually the annual values changes. So here, annual data selected, we have a variable in O2 do the plot. So couple of arguments necessary here. X-axis sets to longitude, y-axis sets to latitude, and time axis or call sets to time. Call wrap sets to 3. We want to have 3 images in each row, And then the next one is the robust sets to true to avoid the impact of outlier values on the quality of outputs. So let's run a code, and after a few moments you can see we have actually a multi-layer plot, a multi-layout plot that shows the nitrogen dioxide for each year separately. As you can see, in 2020, the lowest amount of the nitrogen dioxide detected because of the COVID-19 situation, and now it's very easy to interpret this situation. So you can do this or apply this for all around the world, but typically it works for the areas with a dense situation and very populated regions with high amount of industrial activities. So maybe for a smaller urban area, not working very well. So because of the spatial resolution is a little bit coarse, and the size of the city and the size of the industrial activity also matter in this tutorial. So then in the next system, I'm gonna show you how to make a plot that that reflects the average NO2 variations from one year to another year. So because sometimes we want to have some plots to see the visual change, and sometimes we need to have a plot to show the temporal variations and compare a year with another year with a better accuracy. So now I'm going to calculate the average of NO2 over this study area in each image separately. So here we will have the previous variable was the annual. Now I'm going to have the annual average. So the annual average sets to get the annual data and calculate the average over longitude and latitude. Longitude and latitude dimension. Annual mean, here it is, and now you can see we have actually the average value for each year, the average NO2 value for each year separately. So it is better to convert it to a data frame structure because longitude and latitude no longer available. So it's very easy to do here. Annual data frame equals to get the annual mean and convert it to a data frame structure. There it is, the annual data frame. We have a data frame including two columns that shows the nitrogen dioxide variations from 2018 to 2024. It's very easy to make a plot like annual df dot plot, just like this. And here you can see the annual variations. In 2020, the amount of NO2 clearly dropped, significantly dropped and decreased compared to the other years. So, and even you can calculate the anomalies to actually see the differences much better. So make another line of the code and do the calculations for the anomaly. So we want to have a new column in the annual DF, the annual data frame, a new column as, for example, anomaly created, sets to get the annual data frame NO2 values subtracted from the average NO2 value, NO2 that's min. There it is. And now you can see a new column added as anomaly that shows where the NO2 values is above the average or when it is below the average. So let's make another plot for the anomaly. So here it is, the annual data frame dot select the target column. Here is the anomaly and do the plot again. So as you can see, the values below the zero actually showing or reflecting the actually showing reflecting the uh, significant decrease in the nitrogen dioxide in 2020 compared to the other years. Even you can make a bar plot, plots dot bar. Let's run. Here it is. You can see for the 2020 uh, clearly the amount of the nitrogen dioxide decreased because of the quarantine situation and stopping all industrial activities in this year. So, and you can see it is very easy to do these kind of calculations, but I forget to show you how to get export from these maps and plots. It is also very easy process to do. For example, imagine that you created such interesting plot and you want to get export. So first of all, we need to import the matplotlib, a typical library for dealing with the plots in the Python. Import matplotlib dot pyplot as plt. Okay, now in the next step, use the plt dot savefig to actually make to get export from the annual map layer. So this is the annual NO2 average NO2 with PNG format. Let's set a DPI explaining the resolution of the output could be 360, typically offers a good quality. And the next one, what is the next? The next one is BB box inches. Sets to tight, guarantees everything included in the export, in the exported map. So after a few moments, you will have a new plot. You can download it from the left panel. Just set an address and save the output. You can see the output with a good quality, everything included, and also it has a very good quality. You can use it in your own report or study. So you can do the same process for the next step also. The same process and the same code here can be used for the rest of the plots. For example, here I can use the plt.savefig again. .savefig. This one is anomaly map. .png format DPI 360. And the next one, the DPI 360 BB box inches sets to tight. There it is. Let's run, and then anomaly is available. Let's run the anomaly and save it like this. It's very easy to do, and also dealing with the Earth observation satellite data in the Python, you will have access to several resources that typically not available in the Earth engine, but here we can do a lot of things thanks to the XR library, Xarray library, and also the XEE. And also it is possible to make a monthly map to see how NO2 varies from one time to another time. You can also do the analysis in the sub-annual scales. So as you remember here, we had a variable. It was the first variable was the data set, the nitrogen data. Now we can convert the data set to the weekly or even monthly format and see the how NO2 varies from one year to another, year in a subscale. So make a new variable. Here it is the monthly. Get the DS data and do the resample. For time dimension, the time dimension sets to months and calculate the average through the time for each month. So let's run a code. In the monthly scale, as we will have a large number of images compared to the annual one, definitely takes a bit more. Maybe takes 2 or 3 minutes or even 5 minutes. You must be patient until the monthly average is created. Now, as you can see, after 2 minutes it's done and 78 monthly images created. Let's do the plot. The monthly, but remember that we need to get the average of each month for the region of interest, and that's why we need to calculate the monthly average. Here it is, the monthly that calculate the average over the region or a spatial dimension. So here it is, the monthly average created. Let's convert it to the data frame structure, the monthly mean to a data frame, because the spatial dimension no longer available here. So now let's make a plot, monthly data frame dot plot. Here it is. You can see this is the monthly variation. In 2020, you can see we have a big drop or significant drop in the nitrogen dioxide. And also it is possible to highlight the NO2 values for 2020. Let's make a filter here or make a query and select the NO2 values only for 2020. Monthly 2020 from the monthly data frame. Now make a bracket monthly data frame dot index dot year. Select those data belongs to 2020. So this is a simple query. The monthly 2020. There it is. Only the data for 2020 listed here. So let's make a plot. Fig x plt dot subplots. I'm gonna have a plot with this figure size. For example, 10 widths and 4 heights. And then x dot plot first monthly data frame index for the x-axis, monthly data frame NO2 for the y-axis. Let's run, and we want to have another plot that should highlight the values for 2020 COVID year. So again, x, the same x, do the plot. This time monthly 2020 index monthly 2020 dot NO2, just like that, and let's run. And here you can see this year, the COVID year, highlighted in the plot, and you can see it's a clearly lower value, offers a lower value because of the lower fuel consumption or industrial activities in this year. That here you can see how it is easy to do the multi-temporal analysis for the air pollution using this data. And also it is also possible to calculate the amount of the change or amount of the decrease or increase regarding to the air pollution in the annual scale or weekly scale. For example, here I can for the annual scale I can show you how many percent decreases or how many percent increases here. So the variable name is the annual data frame. Let's make a new column, for example PCT, percent of change, equal to the annual data frame. Select the column name, for example the NO2 dot PCT change, the percent of change calculated here. So here you can see the percent of change calculated. Let's make a plot from PCT values, and here also shows the amount of percentage. So you can see it's about 10% decrease detected in the 2020s, and it is easier to interpret that, say, for example, in 2020, the 10% of the nitrogen dioxide dropped by 10%. So it is really, really easier to understand and also for the interpretation. Here in this tutorial, you learned about a bunch of techniques and methods for the air pollution data analysis regarding to the COVID. And also remember that you can apply or extend this tutorial and also this technique for the rest of the megacities or metropolitan areas in all around the world, and not only limit yourself to one location. Let's try this tutorial for another big cities in all around the world and see how the nitrogen dioxide varies from one year to another year. I hope you like this tutorial, and I'm asking you to share this tutorial with other people who are interested to remote sensing techniques. Thank you for the attention.